Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today our topic will be tangent planes and linear approximations. Okay, let's think back a minute here. Calc 1, the idea of a tangent line, right? It was fundamental to Calc 1. So here is a function of two variables. That should be a little smoother down there. And you have a point where it's differentiable. Draw the tangent line, right? If you zoom in there, what happens is that the tangent line and the curve become indistinguishable, essentially, right? So you zoom in, right? And maybe I'll draw the curve in black and the tangent in red. First of all, you zoom in, the curve looks sort of a lot less curvy there. That's one thing that happens. And the line is always a line. It's straight no matter what. But when the curve gets less curvy, the line looks like it hugs the curve tighter. That's not a very good picture, but you get the picture, though. The curve looks like a better approximation, or I'm sorry, the line looks like a better approximation to the curve. That was a very fundamental idea from Calc 1. For a differentiable function, it is one where the tangent line is a good linear approximation locally to the curve. All right, well, let's now consider a surface. Not so easy to draw here, but if we have a 3D surface, we can do the same thing. If it's differentiable, we can pick a point, right? And rather than having a tangent line there, we have a tangent plane. In other words, some flat plane that does a good job of approximating the function's behavior at that point. I don't know if we can see this here, but so the marker here is something, maybe a surface, something like that, right? It's not flat. It's got some curvature to it, and we can clearly see that from looking at it at a global view. But if I'm a little tiny bug on the surface of the marker, as I walk along, maybe I don't feel that curvature, just like people walk along the surface of the Earth. The Earth is curved, but we don't feel it. It feels flat. Same idea with the marker. I can put a tangent plane at any point on here, and that plane is flat. And if a bug crawling along the marker surface were to start crawling on that tangent plane, it wouldn't immediately realize it was off the surface. The surface and the plane are close together locally, right? Same idea. You can run tangent planes to, say, the Earth's surface, some kind of sphere, and you would make it look flat from there. Okay, so let's see how we do these things. The development is really rather similar, though we have to involve some partial derivatives here. So here's a surface, f of x, y, and let's give it a point, x naught, y naught, z naught. Right? The tangent plane, one thing about it is it contains the tangent line to any space curve that lies on the surface and passes through p naught. So let me say that in writing. So tangent plane of z at p naught, it contains all the tangent lines, essentially. It contains the tangent line to any space curve r of t that lies on z and passes through p naught. Passes through p naught, right? So a bunch of curves lie on z, lots of them pass through p naught. Each one has a tangent line, tangent vector, right? All those tangent lines make up the tangent plane. All right? Okay, what more can I say? So the curve passes through p naught, so r of t naught is p naught for some t naught. All right? Then the tangent line to that curve at p naught is parallel to r prime of t naught, right? So r prime of t naught is the tangent vector to r of t naught, right? If the tangent line is there, it's parallel to that. It's just a line that runs through this vector, right? Okay. All right, so in the last section, the last thing we did was we considered implicit differentiation, right? and we talked about considering surfaces as level surfaces of 4D functions. Let's take the same exact approach now. So actually that was a good lead-in to do that in the last section. Let's consider this. Do I want to erase? Yes, I'll erase. Let's consider this surface as a level surface of something 4D function, and let's call it W equals f of x, y, z. Right? So same trick we pulled last time. For example, if I had z equals x squared plus y squared, I would just consider my W to be x squared plus y squared minus z. Right? This is the level surface of W. Right? Okay. So the curve r of t is on the surface z, which means it's on this level surface, right? So curve r of t on the level surface, f of x, y, z equals 0. The point of this is that in the section on gradients, I guess that was actually the last section, the gradient section. The gradient section, we talked about how on a level curve, the gradient and the tangent vectors are orthogonal, right? Well, the same exact calculation works for level surfaces. So we talked about level curves. The same exact calculation works for level surfaces. So in other words, the gradient, and let me make a change here. Yeah, no, we'll keep f. No, we better not. We better make this big F. Better make this big F. All right, so, and I guess I really want a big F here too, don't I? Yeah, okay. So I want big F. So this gradient is orthogonal to r prime at each point on the level surface. Right? In other words, the gradient here is orthogonal to this vector. That's the same thing we had in the last section. And this each point, that includes p naught, right? So including p naught, right? So if the gradient's orthogonal to the tangent vector, what does that mean? It means that the gradient at p naught is orthogonal to r prime orthogonal to the tangent line, to r of t at p naught. Right. Okay, so the gradient's orthogonal to the tangent line. The tangent plane contains all the tangent lines to these space curves that hit p naught, right? So if the gradient is orthogonal to the tangent line, right, and the tangent lines make up this plane, right, this guy is the appropriate normal vector. He's the guy we want to be orthogonal to all of these tangent lines, right? Because they all lie in the same plane. This vector is orthogonal to this one, orthogonal to all of them, right? So this is the appropriate normal vector to use. So therefore, grad f of p naught is the appropriate normal vector. Right. Okay. So now we're in good shape because we need to have the equation of a plane, and to do that we need to have normal vector and a point, and we have both those things. So our normal vector is the gradient. What is the gradient? The gradient is a partial f, partial x, p naught times x minus x naught, right? And remember, a p naught was x naught, y naught, z naught. It's sort of, I better say that over here. Did I say it earlier? I think I did say it earlier, but we'll say it again. That's p naught, right? So the gradient is the partials in order, right? So the gradient of f is partial f, partial x, p naught i, partial f, partial y, p naught j, partial f, partial z, p naught k. So this is partial f, partial y, p naught, y minus y naught. Get rid of this. And partial f, partial z, p naught, z minus z naught equals 0. There is our tangent plane, right? So there is our tangent plane. So this is tangent plane to the level surface. W equals f of x, y, z equals 0 at p naught. Right, equals that. So there is the tangent plane, right? And so in a minute we're going to see how we don't always have to consider this as a level surface. We can make one minor adjustment, but this is good for now. Also, it's worth noting that the normal line of this level surface, of the level surface, W equals f of x, y, z equals 0, at p naught is the line just parallel to the gradient, and it also should be through p naught. So the normal line is sort of like, it's like the weather vane, so to speak. The tangent plane has the gradient extending out of it orthogonally, and this line is the one that happens to cut through the point p naught. Okay, so the tangent plane obviously shifts from point to point, and so p naught is important here. And it's worth noting that the normal line has parametric equations. They're easy to find because we need a parallel vector and a point, and we have them both. Normal line has equations. X naught plus a partial f partial x of p naught t, y equals y naught plus partial f partial y p naught t, z naught plus partial f partial z p naught t, right? So it's a line. It's parallel to the gradient vector, and it's through the point p naught. So those are just the equations of a line. Straightforward. Straightforward. Okay. Now what? I'm going to leave this up here now. Let me get rid of some other stuff down below. Get rid of all this. So let's do an example. How about x squared plus 2y minus z cubed equals 1? Let's find the tangent plane and normal line at point 2 minus 2 minus 1. All right. Okay. So actually, it doesn't matter whether this is equal to 1 or not. That's completely inconsequential because when we do partials, it's going to go anyway. So really, this could be any level surface you want it to be. It doesn't have to be 0. It could be equals to c. So OK, what we need is the gradient. We need the gradient at 2 minus 2 minus 1. This guy is our f of x, y, z. And this is our level surface of our function of 3 variables. The gradient is a 2xi plus 2j minus 3z squared k, evaluated at 2 minus 2 negative 1. Right? Wind up with a 4i plus 2j, and then minus 1 squared is a positive 1. So that ends up being minus 3k. Right. Is that what I have? Good. So the tangent plane is easy. We have the components of the normal gradient vector. All right. So we have a point on the plane. This is plug and chug time. Minus 3z plus 1 equals to 0. And that's 4x plus 2y minus 3z. That's a negative 8. Positive 4 makes a negative 4. Negative 3 makes a negative 7. So you never get equals to 7. That's what I have. Good. And the normal line is also straightforward. Normal line is x equals, where's my point? So 2 plus 4t. Y equals minus 2 plus 2t. Z equals minus 1 minus 3t. Like that. Right? Okay. So that's tangent plane. Now, there's one little adjustment to make. Normally, not normally, but maybe oftentimes we're given z equals a function of x and y, and we ask what's the tangent plane to that. Well, there's not a lot of difficulty in making the transference here. So if we have z equals f of x, y, right? Then how did we get a level surface of 3 variables? Well, we just took a minus z from both sides, right? Just took a minus z from both sides. You move the z over, you get that thing, right? And so if I take, so if I consider this to be a function of 3 variables, now that's my big F. That's a function of 3 variables. There's my level surface. If I take partial derivatives, I get, well, partial big F partial x is just partial little f partial x. And there's no x's and y's over here to mess this up. Partial big F partial y is just partial little f partial y. And what's partial big F partial z? Just minus 1, right? Because this is just a minus z. So this just becomes a minus 1 up here. So sort of the more common way to see this maybe is if we have just a surface given as a function of x and y, z equals f of x, y, at a point x naught, y naught, z naught, then everything is the same as above. And this is p naught. I don't know why I'm using that. All right. So there's that. Partial f partial y, p naught, y minus y naught. And then this over here is just minus z naught equals 0. So this is sort of more your more standard version of this, what you would see if you had just a typical surface defined as a function of x and y, right? Okay, example? Yeah, let's do an example. Let me get rid of this. So let's say we had a z equals x cosine y minus y e to the x. Let's do the point 0, 0, 0. I need partial f partial x at 0, 0. Partial f partial x here is a cosine y minus y e to the x at 0, 0. Cosine of 0 is 1. Minus 0 is also 1. Partial f partial y at 0, 0. This is x minus x sine y, and minus e to the x at 0, 0. So now I dump things there. This becomes 0. This becomes minus 1. Yes, it looks good. And so as a consequence, x minus y minus z equals 0. Is the right tangent plane equation. Yeah, so that's the tangent plane. It's nothing to do with z there. The nice thing is, though, this is two different perspectives. This is if z is solved as a function of x and y explicitly. We can also handle the problem, though, if z is not a function explicitly. If it's implicit, we can still get a tangent plane equation. So it's nice to have two different perspectives on this. I think that's a good thing. One note, we talked about differentiability previously, and we saw that kind of funky example where you had the elevated cross, everything else was down below. That guy was not differentiable at 0, 0 because it didn't have a good tangent plane. It's like in single variable calculus, those functions that are differentiable have a good tangent plane. In other words, they have a tangent plane that describes the behavior of the function well locally. If you don't have a tangent plane that does that, you're not differentiable. That cross didn't have one. You couldn't lay a good plane there because any plane you laid would be poor as far as the behavior went. A plane laid on top of the cross would only catch the cross. It wouldn't catch the behavior in the cracks. All right. Another example. Let's try a couple surfaces here. Here is a surface that's a paraboloid, elliptical paraboloid. And here's another surface, which is a plane. And this paraboloid and this plane intersect in an ellipse. I will now attempt to draw this in quality form here. There's the plane. That part's the easy part. And let's see here. Maybe I'll use a different color. How about that? So over here is sort of this thing. There's the top of the paraboloid. And maybe it's coming sort of down like that. And maybe it's sort of coming down like that, right? And as it bumps into the plane, there's an ellipse formed, right? So in other words, that ellipse is where the paraboloid cuts into the plane. That's not too bad, really. And your z-axis is sort of maybe coming out like that, right? These guys, excuse me, intersect in an ellipse. And one point on that ellipse is the point 1, 1, 2. I'd like to find the tangent line to that ellipse at that point. So in other words, what is the tangent line to that ellipse at that point? What I have here are sort of two level surfaces, right? I've got one level surface that looks like this. That's equal to 0. That's 0 there. It's x plus y squared minus z. That's the parabola as a level surface of a 3D function or a 4D function. And then my g, my other function, right? This guy is just y plus z equals 3. That's another level surface of another 4D function. There's just x is allowed to range totally free here. Right? That makes sense. OK, so this tangent line lies in both of these guys' tangent planes, right? It has to, because it's the intersection of two surfaces. It has to lie in both their tangent planes, right? So this tangent line, it is in both surfaces' tangent planes. Therefore, it's orthogonal to both surfaces' gradients, right? Because the gradients are all orthogonal to the tangent plane. If you're orthogonal to this guy's plane, I'm sorry, if you're in this guy's tangent plane, you're orthogonal to this guy's gradient. If you're in, keep using little f when I want to say big F. If you're in this guy's tangent plane, you're orthogonal to his gradient, right? So you're orthogonal to both gradients at 1, 1, 2. If you want a vector that's orthogonal to two things simultaneously, pick the cross product. All right? Therefore, the tangent line is parallel to the cross product grad f cross grad g at the point 1, 1, 2. Right? So again, this cross product is orthogonal to both those guys simultaneously. Right? So let's keep working over here. Let's get these gradients. Grad f ends up, where am I here? So it's 2x I plus 2yj. We got a minus z over here, so I got this minus k to deal with, right? And I put in 1, 1, 2 there, and I do get 2i plus 2j minus k, right? That is my grad f. Okay. Grad g, on the other hand, all right, so there's no x term at all, so there's nothing, no I component. This guy is just j plus k at 1, 1, 2, which is just j plus k. There's nothing even to evaluate there. Makes sense because the gradient of a plane is the gradient of a bunch of linear terms. It should be constant, right? Because a constant direction is increasing on this plane at any given point. So let's do the cross product. Let's do the cross product. Here's I, here's j, here's k. 2, 2, minus 1, 0, 1, 1. There are your gradient vectors. You can hash this out. 2 minus a negative 1 is 3, and 2 minus 0, and then add that extra minus on there for the j term, and then 2 minus 0, so we end up with plus 2k. That's what I get to. Good. So that guy is our parallel vector. Tangent line now has equations, right? These guys are the parallel vector. The point is up here. So I get x equals 1 plus 3t, y equals 1 minus 2t, z equals 2 plus 2t. Yes. And we can take note that the plane was y plus z equals 3. So lo and behold, y plus z is 1 minus 2t plus 2 minus 2t, which is 3. This tangent line does lie in this plane. It should, right? I mean, anybody that's tangent to an ellipse in the plane better lie in the plane itself. So the tangent line does lie in the plane. Okay, good. So that's that. Linear approximations. All right, here goes. Let me make some room here. Really, here things are, we've done a lot of work with this in Calc 1 already, so we have some good notion of what's going on. A tangent line gave us a way of doing a linear approximation in Calc 1. The tangent plane will give us a way of doing a linear approximation in Calc 3. The goal was the same. Take a complicated function, replace it with a linear one at a point, so that when you travel locally, the tangent or the linear approximation and the function are approximately the same. All right, here goes. So here is the world of xy. XY plane at some point, right? Say you don't want to travel too far away. You want to go x naught, y naught nearby, right? Your change in y is a y minus y naught. Your change in x is x minus x naught, right? My goal, also I should make a note here, x naught, y naught better be differentiable. Let me say this here. Hold on. So here's a function f. It better be differentiable at x naught, y naught for this to work. right? In other words, there should be a tangent line approximation near there. Yes, okay, so I'm starting here, and I'm going to, so this is the starting point, this is the nearby point. X naught, Y naught is the starting point, this is the nearby point. Okay. All right, so at differentiable, I find a nearby point xy, goal, approximate f of xy, right? Here I'm moving delta x, so this is movement in the I direction, right? In the x direction. This guy is movement in the j direction, like that, right? So what are rates of change? Well, if we move strictly in the I direction, then we're talking about partial f, partial x. In fact, we know that partial f, partial x is changing constantly, but if we don't move very far and we look at partial f, partial x at this point, then if we're not traveling very far, the derivative is probably going to stay pretty steady around that point. It shouldn't get too far off. The same idea that on a single variable curve, if we go far from a point, it's a lot of change in the derivative. When we stay close to it, not so much. Same idea here. The rate of change in this direction is partial f, partial x at x naught, y naught, right? And similarly up here, I can get rid of some of this. If I move in the j direction, my rate of change in this direction is a partial f, partial y, x naught, y naught. All right? Okay, here goes. So linearization. The linearization L of xy of the function f of xy at a point x naught, y naught, so that's a mouthful. So the linearization of a function at a point x naught, y naught, right? So we're now linearizing. We're developing a linear approximation here. What is it? Well, in fact, let me start farther over so I can, it's kind of a long thing. Right? Where do we start on the surface? Well, the function value, right? So this is your starting point. So this is the initial point on the surface. All right. How much is z changing as I move this little bit in the x direction? Well, it's changing approximately by this rate of change times this movement. Remember, what am I saying here? It's like a d equals rt idea, right? So in other words, how far am I going on my surface being moved? Well, my distance on my surface being moved is my rate of change, which is this guy, times the time I'm moving, which is this amount, right? It's an approximation because this is actually changing as I move along in points, right? But if I don't go very far, this stays pretty steady. It's not going to change a lot. So I've got this partial f, partial x at x naught, y naught piece times x minus x naught, right? This is the approximate change in z as you move delta x in the I direction. Right? In other words, this is the rate of change, And this is the amount of stuff you move. And if this is pretty small, then this rate of change could stay pretty constant, that we feel like this is a pretty good approximation of how far you moved. And similar gig on the y direction, you move at some delta or partial f, partial y, you move in a delta y distance or a time. You wind up with this approximate change in z as you move delta y in the j direction. Let me get out of the way here. So this is what you look like. In other words, just like with a tangent line, you move a little bit in the x direction and you figure the derivative is a pretty good, steady approximation here. There's not going to veer around a lot. This function is certainly linear, right? It's going to be, here's a constant. This will be a constant x, another constant times y, another constant. This guy is linear, right? And in fact, it is the linear approximation. So the linear approximation is the output of the linearization. L of xy, or let me say this. So a linear approximation of f of xy is the value of L of xy for xy near x naught, y naught. So this is the linearization. It's an actual linear function of x and y. Its output is the linearization. So there's sort of two distinct things there. Same as in Calc 1. The linearization was the tangent line. Its output is the linear approximation. And just like in Calc 1, the farther away I get from x naught, y naught, the less valid this becomes, because these derivatives will change, and they're going to change more rapidly than we're accounting for example, and we're going to get off of our approximation very quickly. So this is valid for local things. All right, example here. So here is a function of two variables, y to the sixth plus e to the xy. Let's pick a point, 0, 1. I'd like to find the linearization of this and use it to make some approximations. Right. And sometimes it's worthwhile to label this. I mean, depending on the point you pick, the linearization will be different. So you could label this like L sub 1, 0 if you wanted. You don't have to, but you could do that to show that this is based off of that. When I plug in 1, 0 to this function, I get e to the 0, which is 1. All right. And then I need partial f, partial x. That means that I need y e to the xy at 1, 0 times x minus 1. Then I need partial f, partial y, which means I need 6y to the 5th plus x e to the xy at 1, 0. Run out of room here too. Y minus 0. So here is partial f, partial x at 1, 0. Here's partial f, partial y at 1, 0. And then I'm looking at how far we are from 0 in the y direction, how far we are from 1 in the x direction. All right? And if you crank this out, this winds up giving you 0. So this whole term is gone. And this winds up giving you 1 times e to the 0, which is 1. So really wind up with 1 plus y. Pretty nice linear approximation. This is very straightforward. But it is a function still of x and y, just x is able to range free. Okay. So now let's pick a point. Pick a point near 1, 0 in the xy plane. That is to say, you're choosing a point where delta x and delta y are small. You're not moving very far away. So I'll pick 1.1 and 0.1. So delta x and delta y are both a tenth away. Okay, that's not too bad. That's pretty close. Then if I plug in those points to my linear approximation or to my linearization, and I'll plug them in up here, right? I get 1.1, right? So plug in y, and 1 plus 0.1 is 1.1. So this is linear approximation. This is the linear approximation of 1.1 comma 0.1, f of those points. This is the linear approximation. In other words, this is what we expect to be pretty close. And if we check things out, we can actually plug this guy in. We do get 1.1163. That's pretty close. I mean, you're accurate to the tenths place. Maybe you could do a little bit better if you went closer. But certainly this is not too far off of our actual value. All right, so we're off by 0.0163 there. OK, one more statement here. I've been saying before, well, we know this anyway, even without me saying it, that the linearization of a function in one variable is a tangent line, if it exists, right? Well, our expectation is this linearization should be the tangent plane. Let's just confirm. Suppose z is f of x, y here, right? And we got a point z naught, which is f of x naught, y naught, right? Let's look at L of x, y again a minute. I'm going to erase this. Right, L of x, y is the partial x of x naught, y naught times x minus x naught plus partial y x naught, y naught times y minus, oopsies, y naught, and then we add on z naught at the end, right? So z naught's f of x naught, y naught. So it's just L of x, y written in a slightly altered form. So how can we see, suppose we called this a surface. Suppose we called it, what can I use? Let's use capital Z here. So I make that really big and bold to distinguish it from small z, right? So let's call this guy capital Z. This is the tangent plane to the surface little z at f of x, y at x naught, y naught. Why? Because if I set capital Z, is capital Z here? Well, really, so to avoid confusion, capital Z there, it's huge. So capital Z is 0. What does that mean? It means that I got 0 equals a partial f, partial x, x naught, y naught, x minus x naught, plus partial f, partial y, x naught, y naught, y minus y naught. And then if I wanted to, I could move this z over, right? So I could have a minus a capital Z, and then a plus a z naught. Well, I could rewrite that. Hold on. So I could rewrite plus z naught as minus a negative z naught, right? And these guys are exactly the same, right? Big Z is equal to little z exactly at this point, right? It's a tangent plane. So the one place that the plane and the surface come together, or maybe the one place, but at least the one place they come together, is at big Z and little z, right? Or is that z naught? So the one place that big Z and little z come together at the very least is at z naught. So I can take this big Z and make it a little z, right? So it used to be a big Z, now it's a little z, because these are the same when this is the point in question we're talking about here. And this is exactly the tangent plane equation that we had before for a surface z equals f of x, y, right? So in case of The surface's linear approximation is a tangent plane approximation, and the linearization is, in fact, the tangent plane. So linearization is, in fact, the tangent plane. Okay, that's it.